Okay. Okay. So I think we can start. Hi, everybody. It's a pleasure for me today to introduce you Dr. Agnes Kospal, and I'm going to say a few words before starting. So she defended her PhD thesis in particle physics and astronomy summa cum laude at the Ethos Lawrence University in Hungary in 2009. And after that, she was an assistant researcher fellow at Konkoly Observatory in Budapest, Hungary. Then she was a postdoctoral researcher at Leiden Observatory in the Netherlands, and always in Leiden, she wore the prestigious ESA fellowship working at ESSEC. Finally, she moved back to Hungary, being a senior research fellow until 2019, and when she became researcher advisor, tenured. And this is her current position at the Konkoly Observatory, the Research Center for Astronomy and Earth Sciences, where she leads the Star Formation Group. During her career, she won many awards and funds. She has been really successful. I just mentioned the fact that she won an ERC starting grant, which just finished. His name was Sacred, was about accretion and variability. And her commitment in being a female role model for young researchers. She tutored many students like postdocs, including me, and she's part of many international collaborations. She's a well-recognized expert of star formation in general and variability in particular. So for this reason, I will stop this presentation here and I leave to her describing her work. So please, Agnes, the resource.
Thank you very much. Thank you. I'm sure this is much more flattering than what I deserve. But thank you very much for the nice introduction. Thank you for the invitation. It's a great pleasure to be here. This is my first time in Naples, so I'm really happy to be here and to meet you. Yes. So today I'm going to talk about the variability of young stellar objects. And but first, it's going to be a long talk. So just to summarize what I'm going to talk about, I will give you a short introduction to Konkoly Observatory, from where I come, and then a little bit of introduction to star formation, because I know that not all of you are working on this topic. And then I will talk a little bit about variability of young stellar objects, why we are interested in this, what are the physical reasons for the variability, how we can observe this, and what physical parameters we can constrain from these observations. And then I will focus on kind of a parameter space, which is the time scale and the amplitude of the variability. And then there will be different groups of young stars in this parameter space, and I will talk about each of these groups. Each of them are interesting for their reasons. And then one aspect that I will mostly focus on is the most extreme variability, which are the outbursts and their effects on the circumstellar matter, which is the specific field I'm studying. So I will talk a bit more about that. So just to start off, I'm coming from Konkoly Observatory. This is the main and largest astronomical institution in Hungary. It's, as Elena mentioned, part of this Research Center for Astronomy and Earth Sciences. So there's the Astronomical Institute and two more Earth Science Institutes grouped together, with some collaboration between us, and it belongs to a larger network of basic research institutes that previously used to belong to the Hungarian Academy of Sciences. Now it belongs basically directly under the Hungarian government. At the moment, we have 65 astronomers working at our institute. It's really a large institute. 25 of them are permanent staff. And then we have at the moment 19 postdocs, 21 PhD students, 6 professors emeriti, and some support staff. And it's quite international. And typically, like a fourth or third of the staff, or the researchers at least, are international. And then we work on various topics. So, of course, one topic is stellar physics. So there are colleagues who work on stellar pulsation, stellar activity, nuclear astrophysics. There's another ERC group which run at the same time as my group. for nuclear astrophysics, and then we work on circumstellar environments, so star and planet formation, exoplanets. There's a group for solar system studies, so they study asteroids, trans-Neptunian objects, even meteorites. And there are a few people working on extragalactic astronomy, supernovae, quasars, and also the large-scale structure in the universe. It's a new research group, and then there's a little bit of instrument and satellite development. I have a colleague who builds CubeSats. So that's basically what our institute is working on. And that is our main building where also Ella used to work. And we also have a mountain station about 100 kilometers from Budapest. So this is in Budapest, the capital city. And then about 100 kilometers from there, we have a mountain station where we have smaller optical telescopes, basically for three main instruments in these three domes and the residency there. But of course, we are using international facilities as well. We write observing time proposals, and we use the VLT, use other telescopes. I wanted to also talk a little bit about our collaboration with the Italian colleagues. So basically, we started, I think, mainly with Ella, who came to Budapest and encouraged us to build closer connections with people, mainly in Naples and in Rome. And then this is basically our large group who, out of which now some people left, but we are still collaborating, and we have basically weekly telecons, and our main topic, so for this collaboration, for these people, are photometric and spectroscopic follow-up of Gaia science alerts, and not only these objects, but also other young stars as well. And then if you haven't heard about Gaia, this is the satellite. It's an astrometric mission of ESA. So it basically scans the whole sky several times a year and makes very precise astrometric measurements. But it also measures brightness for billions of stars. And it has an alert algorithm which checks the brightness of each source it measures. And then if it sees something interesting that might be interesting for the scientific community to follow up, then it issues alerts. Like it published, there's a web page where you have some kind of light curve published saying that, okay, this we now publish, and then if someone is interested, they can follow it up. So we are doing that. And then we write joint proposals for telescopes like the LBT, REM, TNG, so facilities which are maintained or funded at least partly by Italians, but also for other telescopes. We are using Hungarian telescopes as well, and then we write joint papers. So what are we working on? So we studied star and planet formation, and you may wonder why is this an interesting topic? I think it's very interesting because, well, I mean, it's clearly interesting because star and planet formation, open questions in star and planet formation often motivates the construction of the largest telescopes and the most sensitive instruments. And then now there has been a lot of development, a lot of improvement of observational and numerical techniques in the recent years, which means that now we have a good general idea of how sun-like stars and their planetary systems form, which is based on basically observational evidence, and the underlying physics is understood using theoretical work and numerical simulations. And then like a broader motivation is that basically by studying stars and planets that are forming now in different star-forming regions in the galaxy, we hope to understand better how around Sun, solar system, and around Earth formed several billions of years ago. So I'm trying here an artist's impression of what a young star looks like. But of course now, because we have fantastic instruments, we have direct images, spatially resolved images of the star formation process, most of the important steps of the star formation process. So I'm showing that here. I've just collected some nice real images of how this process happens. And then basically if we concentrate on sun-like stars, so stars which are less massive than about 8 solar masses, so low and intermediate mass stars, this starts up with a giant molecular cloud where we have kind of filaments where the densest parts they collapse under the gravity, and we get cloud cores, and then at the center where the density is the highest, you start forming a protostar. And then at the beginning, it's still embedded in its envelope, but due to the conservation of angular momentum, the material closest to this forming star quite quickly forms a disk, an accretion disk, which feeds material to the forming star. And this disk also becomes the birthplace of planets. And once you start forming large enough planetesimals of planets, they start interacting with this disk that is their birthplace, and then cause interesting structures. But eventually, you build up your star, you build up your planets, you use up all the material, but the rest disperses, and what remains is basically a mature exoplanetary system. And then I'm going to focus on basically this right-hand side of this graph, or series of pictures. For those objects which we call class 0, class 1, and class 2, these are the objects where we have the protostar, and then we have the circumstellar material. So if you want to observe this kind of objects, then you can measure them at different wavelengths, and then you will find that at the earliest phases, at the class 0 phase, this is the phase where the object is really large, quite cold. This phase lasts for about 10,000 years after the start of the gravitational collapse, and accordingly, according to the temperature, basically these objects are mostly seen at far infrared millimeter wavelengths. And then as it progresses further, after some 100,000 years, you start seeing the photosphere of your protostar, and then there's a lot of infrared and millimeter, submillimeter excess, which comes from the disk, the circumstellar disk on the envelope. So now you have that higher temperatures, of course, but it's still quite large because these envelopes can be pretty large. And then even later, the envelope disperses. What you have is basically your protostar and photosphere, and then some excess from the disk, which can still accrete or can be passive after a while. This may last for a couple of million years, and these disks are typically 100 AU in size. And again, you still have some temperature gradient, and after a while, as the accretion stops, you disperse your disk, and then you basically have your star, and then even later, like after tens or hundreds of millions of years, you may have some collisions between your planetesimals, and that may produce fresh dust in this system, like a dusty disk, which we call a debris disk. So those disks are signs of planet formation, and then that lasts for a long time. Even the around solar system have a debris disk. So so you saw that this is a quite complicated process with many details. And then one difficulty about observing and modeling these systems is the problem with the orders of magnitude. So if you look at spatial scales, the filaments that we have in the molecular cloud are several parsec long. So you have to take some material which is spread out at several parsecs, and then you have to compress it to basically one solar radii, because that's the size of your star, and that's I think 8 orders of magnitude you have to overcome. And then of course in the ISM, in the interstellar matter, you have densities which are typically like 1,000 particles per cubic centimeter, and then you have to increase that density to 10 to the 26 per cubic centimeter, which is the density at the center of your star. And then for the temperatures, you take the interstellar matter, typically 10K, and then at the center of your star you have 10 million. But even if you disregard the star and the stellar interior, which I don't work on, and we only look at the circumstellar matter, there are still orders of magnitude variations in densities, in temperatures, in different physical parameters. So this evolution I outlined, it takes a few million years, but of course we don't live that long. But we do see variability if you look at a young star at shorter timescales, which is very nice, because that's a good topic then for a PhD or a postdoc. And indeed, young stellar objects have been defined many decades ago as variable stars. They were recognized variable stars. And if you look at these traditional variable stars like T Tauri or Tauri, or once you run out of the alphabet, you start numbering them like the 1057 Cygni and whatever. So many of these long-known variable stars are young stellar objects. Typically, these have been monitored at optical wavelengths. 100 years ago, we only had optical telescopes. And then if you monitor this kind of stars, so the low-mass young stars are called T Tauri stars, and the intermediate-mass young stars are called Herbig stars. Virtually all of them are irregular variables, and their variability amplitude spread from the barely detectable to 5 magnitude or even higher. And then, of course, there are different reasons behind this variability, which then cause different variability patterns. So again, I'm showing an artist's impression of what a circumstellar environment of a young star looks like. And then if you look at different parts of this system, then you may notice accretion channels through which the accretion rate may be more efficient or less efficient, more or less material may go through this, and that means that that changes the energy that is released when the material lands on your star. So that causes variability. And then there may be flares, which are the analogs of the solar flares that we observe in our sun, but for young stars, because they have much stronger magnetic fields, it's much more energetic. And then if you look at low mass stars, again, because of their magnetic activity, there may be dark stellar spots on them, and as the star rotates, then that also causes some variability. And then, of course, there's a lot of circumstellar material around your young star, and then if the inclination is so, then parts of the material may obscure your star, and that will also cause some variability. And then, of course, all of these things may happen at the same time. So how do you deal with that? I mean, there are some objects where this can be nicely discerned, not always, but there is this very special case where we managed to do this, and this is called BQ10, one of the young variable stars in Taurus. Here I'm showing a light curve taken with the Kepler-K2 mission. It's an optical light curve which covered about 80 days with a 1-minute cadence. It's a great data set, and we managed to discern the different variability phenomena here. So with very light gray, we see a kind of a sinusoidal variation, which is due to the rotational modulation caused by the dark spots on the star. And then in some cases, you can see that the star is brighter than what you expect compared to this sinusoidal curve. And that's because during those times, the star was actively accreting from the disk. This typically lasts for a couple of days. But then there are these narrow peaks, very bright peaks, which last only a few hours. Those are stellar flares. And in some cases, the star is actually fainter than what we expect, like here, also here. And that's because of obscuration by the circumstellar material. So everything is mixed here. So it's sometimes not easy to discern, to differentiate between these phenomena, but sometimes colors, sometimes time scales help. Now, just to recap what I'm talking about, young stars are variable. They are variable not only photometrically, that I've been talking about so far, but also spectroscopically. And but they have different time scales and different amplitudes. And this graph basically summarizes what are the typical variability amplitudes and typical variability time scales for a whole range of phenomena that we can observe for young stars. And then the color coding basically shows the different phenomena. Like the blue bubbles are accretion-related events. And then there's some longer time scale, smaller routine variability, are slow changes in the disk. There are extinction-related behaviors with the red bubbles. There are some events like when there's a binary and then one has a disk that obscures the other one, or when you have two stars and then they eclipse each other. So those are binary-related things. And then there are small amplitude variability, which are related to the star itself, like the spots or the flares or even pulsations. The young stars may be pulsating variables. So this is kind of an overview. And I'm going to focus on accretion because, again, this is the field I'm studying. And just to repeat again, accretion is the mass transport within the disk and from the disk to the protostar. And this is, again, very complicated. It depends on density, it depends on temperature, ionization, magnetic field, and it varies with time and location in the disk. And in this series of figures, I'm showing kind of an evolution of how our knowledge about this, about protostar accretion developed. So this is like, a simple artist view, which may not be very precise, but then you can just sketch out different parts, like you have the disk, and then the dust disk, and then you have a gas disk, and then you have accretion columns, then the material is diverted by the magnetic field of the young star, and then the material lands on the stellar surface. You have the accretion shock, and then you may have disk wind, you have stellar wind, all kinds of various things. But then that's, again, just a conceptual sketch. But nowadays, there are some groups who really do like 3D magnetohydrodynamical simulations of the accretion process. So this is the result of such a numerical simulation. So these are very advanced things. I will focus on the rest of my talk on accretion variability. So I will focus on the blue bubbles. And you can see that there are like very dramatic events, which have very large amplitude, like 4 to 6 magnitudes. These accretion outbursts. These are so violent that they are important for disk evolution, planet formation. They have long-lasting effects on the properties of the disk. They may even affect the stellar radius. And then there are less dramatic events, like smaller amplitude, smaller timescale bursts, and then like the typical fluctuations of the magnetospheric accretion, which may have less significant effects, but are still important to understand the underlying physics. And then what is important to keep in mind that accretion rate varies throughout premium sequence evolution. So we find variable accretion class 0, class 1, class 2 objects as well. So it's very important to understand this to know how stars gain their mass. There are many open questions in this field, and some of these questions motivate my own science. For example, what is the role of variable accretion in building the stellar mass, and how that will affect the observed properties of the protostars? It's a question whether all young stars experience these large amplitude outbursts, or these require some kind of special circumstances. It's a question of what triggers these large accretion bursts and outbursts. And this is still debated. There are different theories about this. And in some objects, like this one, the 1647 Uranus, you can see that the star brightened, stayed bright for a while, and then went back to quiescence, and then went into outburst again. So there are events where you can switch off the accretion and then switch it on again. So it's a question what kind of process can do that, and how we can use these kind of observations to constrain what kind of instabilities or what kind of physical phenomena lead to these bursts. And of course, in this case, it's also a question how precisely we can measure the luminosity of such a system, which at the top of these bursts may be dominated by accretion. just by taking a light curve at a single wavelength. Probably not very bad. And then what I'm particularly interested in is the influence of the accretion variability on, for example, disk structure or the chemical or mineralogical properties of processes that are ongoing in these disks, which is important because that will, or that may affect planet formation that is actually happening right when these bursts and outbursts happen in the disk. So how can we start to answer these questions? Well, we have to observe these systems, and what is important, and I already mentioned in the previous slide, that it's important to observe them at multiple wavelengths. So use multi-wavelength photometry, for example, and not only like different optical filters, but it's actually important to measure from the X-ray through UV, optical infrared, to the millimeter, and even to the radium. It's very important to be precise. So with space telescopes, for example, you can do micromagnitude photometry, it's great. But even from the ground, there are facilities now with which you can reach millimagnitude level, precision level easily. It's also important to do spectroscopic monitoring because spectra reveal a lot about the physics that are going in this object. Again, there are very interesting lines that trace different parts of the disk and different physical phenomena in the UV or in the optical and infrared and even millimeter. But it's also very, very helpful if you take spatially resolved images with the adaptive optics system, or you use an interferometer. And then if you're very lucky and then the committees like your proposal, then you may be even able to return to a previously observed object and observe it again and try to make interferometric monitoring, for example, super useful. And then all those are the observations, but to interpret them, of course, you will need time-dependent models, which is, again, something that is quite recent. Now people in theory groups start working on time-dependent modeling. So what kind of parameters can we constrain? So time is a key parameter. Of course, we're talking about variability. And if you want to study variability, then basically you have two main avenues that you can follow. Either you make a kind of a large statistical study of a star-forming region, you observe dozens or hundreds or even thousands of objects in a certain star-forming region, and then you do the same for different regions with different age, and then in this way you can follow what's going on as a function of the population age, and then you can do this, you can follow what's happening for millions of years. Or the other thing is that you can do is you focus on a few specific objects, and then you study their variability on an hourly, daily, weekly, monthly, or even yearly time scale, if your contract allows you to do that. So, and then you can observe variable accretion in action. So what is important to understand or to keep in mind is that if you make a snapshot observation of a star-forming region or one specific object, then you will measure properties that are characteristic in that instant. But that doesn't mean that those properties are constant or steady state. You may assume that they are, but they're probably not. So you have to measure this as a function of time. And then I mentioned that I'm interested in bursts and outbursts. So for these, you need to measure their amplitude, what is the accretion rate at the peak, how long they last, how often they repeat, and what is very important is that basically the accreted material over one event. And ideally, we would need to know this for all events. And then, of course, you need to observe the detailed light curves, but you also need spectroscopic sampling, at least at key phases, like at the quiescence, at the peak of the outburst, maybe in between as well, because this will help you understand the physics. So let me just show this graph again, and let me clean it up, so then we only focus on the blue bubble, the accretion-related event. And let's talk a little bit about them. Let's start from the bottom left corner, and there we have the shortest time scale, smallest amplitude variability, which is the fluctuations of the magnetospheric accretion. So typically, this is what the light curves of a classical accreting T Tauri star looks like. And then we make this kind of individual studies of various young stars, typically in Chameleon or in Taurus, in different close by star-forming regions. We have a series of papers on these various individual stars. So what can we learn from analyzing these kind of light curves and spectra? Basically, this is the idea is that the modeling of the accretion shows that young stars can accrete basically in two different ways. One is a stable accretion, where you basically have two well-formed accretion columns, which lends the material from the disk on basically on the magnetic, close to the magnetic poles of the star, and then in such a case, and that is what it stays for a long time. And then as the star rotates, then you can have a kind of a periodic light curve, and then also periodic changes in the profiles of the accretion tracer emission lines. And then the other way is the unstable accretion, where you basically have these smaller tongues of material that can touch the star surface at various places, and then they come and go and reform. And in this case, your light curve will be more stochastic, and then also the profiles of the emission lines change in a more complicated way. And whether a star is like that or like this depends on its rotational period, its magnetic field, it's the strength of the magnetic field, or whether it's dipole dominated or octopole dominated. It may depend also on disk properties, on many different things. So basically, by monitoring light curves and spectra, you can learn about the way the star is accreting. And then one more very interesting thing I'm very excited about now is that you can use this kind of light curves of young stars to try to measure the inner radius of the dust disk. This is called a light echo or reverberation experiment. And this is actually a routine technique in studies of AGNs. So some of you might be an expert in this. But as far as I understand, what they do there is then you have your black hole, which is accreting, it changes its brightness, and then the light travels during some time to this dust torus that is there in the AGNs, and then you can measure that this torus also changes its brightness with some time delay, which is typically weeks or months in case of supermassive black holes. But essentially, you can do the same experiment in case of a young star. You have your protostar at the center, it changes its brightness because the changing accretion, and then the light will travel to the inner edge of the dust disk. It will heat up the dust there, and that heating is actually quite fast. It's almost instantaneous. And then you can observe that basically you trace the accretion rate with optical wavelengths, you trace the brightness of the inner disk, dust disk at some longer wavelengths, let's say near infrared, and then there will be a time delay between their variability, which is on the order of 1 minute, because those are the spatial scales there, but you can try to measure this time delay. And this was actually done once so far in this specific young star YLB 16b. But now we are trying to do this for a second time using one specific young star, which is called DR Tau, and then we are trying to do this with the James Webb Space Telescope using the NIRISS instrument. So this instrument covers the 0.9 to 2.7 micron range, and we complemented this monitoring with the optical light curves like 0.5, 0.4 micron, so we have B and G band measurements. And we measured this star for several hours simultaneously with James Webb. And we were lucky enough because the star showed significant variability, like more than half magnitude just in a few hours. And now we have this kind of light curves at 2048 different wavelengths in this wavelength range. So we are trying to do this echo experiment. I don't have definite results yet, but I think this will work out, but this is still work in progress. So very neat. Okay, let's move on to the next bubble, which are the accretion bursters. These are objects which spend some of their time in coalescence, but then they become brighter from time to time by a factor of few. So again, we have a couple of papers on these kind of objects. Some of the dialerts show these bursts, but one specific system I mentioned briefly earlier, T Tauri, I want to highlight because these show very interesting bursts. This is a very specific system because this is a binary star. It consists of two almost identical 0.6 solar mass stars that orbit each other with a period of about 2 weeks, 15.8 days, and they are on an eccentric orbit, quite high eccentricity actually. But that means that as they orbit each other, sometimes they are very close to each other, they approach each other to within 8 stellar radii, and then other times they are farther from each other. And during periostrons, what we can observe is that the system shows flares, so really brief, like few hour long brightenings in radio millimeter UV and X-ray wavelengths, and then in the infrared and optical, it shows longer brightenings, like they last for a few days. And that's because what's happening is, at least what you can observe in optical and infrared wavelengths, is pulse accretion. So this means that as the two stars orbit each other, when they are at upper star, they are farther from each other, they are closer to the circumstellar disk, they pull some material from the inner disk that will sometime later during periastron eventually land on the two stars, and then the accretion rate increases. This shows a numerical simulation coming from this paper, accretion rate as a function of time for the primary and for the secondary, and their distance. So you can see that when the stars are closest to each other, then there is a peak in the accretion rate. So there's a numerical prediction, and what we actually observe in my paper, we measured this using multifield photometry, and then indeed during most of each periastron, you see a peak in the accretion rate. So it really does that. And then with Ella, we had another close look at this system, not only using photometry, but also spectroscopy. We had 8 spectra taken at different orbital phases. So in this figure, we summarize the accretion rate as a function of orbital phase, and then continuous lines are photometry-based results, the dots are spectroscopy-based results, and the red dots are our results, and it image shows that the accretion rate went up significantly close to periastron. And what is new in this study is that using these line profiles, we could actually discern which star accretes, because these had a high enough resolution to resolve the movement of the two stars. And then from looking at by looking at the accretion tracer lines, we could follow whether the primary or the secondary accretes more. And what we saw is that it changes. It changes from orbit to orbit. It's not always the same star, which actually is what the numerical simulations show, because here you see that one star is supposed to accrete more, the other less, and then they switch here. So very neat. It does what it should do. So, and then one more thing about this system is that, of course, I mentioned that they approach each other, the two stars approach each other very close by during periastron, and that's interesting from another point of view, because they have magnetic fields, and then when they approach each other, these magnetic fields merge. They are so close to each other. And then sometime a decade ago, we had some naive ideas of how this merging and separation of the magnetic fields happen. At that time, we had no idea about the magnetic field of these stars. Now, thanks to spectropolarimetric observations, we could do kind of a mapping of the brightness and also the radial meridional azimuthal components of the magnetic field for the two components separately. So it's very nice. Another interesting thing that we discovered is that if you do these radial velocity measurements from the spectroscopic observations, then of course you can measure these RV curves for the two components, and that actually changes with time. So this is work going back to a couple of, maybe a decade or so, and then this RV curve that you can fit with the Keplerian solution, and then you can get the orbital parameters. Then that changes with time, and that's because the this orbit of the star changes, and that's what we call apsidal motion. So I need to speed up because I only have 5 minutes. So next bubble is the X-loopy type outburst. These are objects which show smaller bursts and larger outbursts. Again, we have a series of papers for the prototype, the X-loopy, and for some other objects among the gyres that turned out to be XORs. Again, I'm showing the light curve from the X-loopy, which is very interesting because it goes back to the 1890s. And then you see larger outbursts, you see smaller bursts. These are the distinction between them. During large outbursts, the accretion rate goes up by about 40. During smaller bursts, it only goes up by a factor of few. And then you can see how the spectral energy distribution or the spectral properties change. It goes from absorption to emission, for example. And then we could study specifically during the large outbursts the effect of the released heat on the circumpolar disk, because both at the surface and in the midplane, the disk heated up. The temperature went up during an outburst, and the temperature was high enough to actually crystallize part of the originally amorphous dust grains that are located in the disk. And then then we did it with Spitzer a long time ago. Now you can do the same with James Webb, much more precisely, and you can also see these kind of spectral features for different solids, but also lots of different molecules we could detect. So you have, this is interesting because you have all the ingredients that you need to make planets and planetary atmospheres. It's really fascinating. And then next bubble, the 1647 Orionis type objects. I showed you this light curve, which goes up and down and up and down. These are multiple eruptions, intermediate duration, mixed spectral properties, a convenient place to park objects that we cannot put either into this bubble or that bubble. So this one specifically, we did some study earlier, and that I'm mentioning because this is our first example where we had repeated interferometric observations with the LTI. At that time, we used MIDI, and then at different times, we managed to measure different visibilities, with which we could fit different parameters for the inner edge of the disk and the envelope, because this is an embedded system, and we could see that on a few AU scale, the inner part of the disk and envelope changed because of the outburst. And then the largest burst or outbursts are the F-Orionis objects. Here you can see some light curves of the first 3 objects that were discovered. The prototype F-Ori, this was the first, and then 1057 Cygni, second one, 1515 Cygni, the third one, and then the black parts are the historical light curves from the literature, and then the red parts are the ones that we ourselves collected and analyzed with my colleagues in a series of papers. And then again, some of the gyres that we are studying turned out to be FUORs. So here you can see that the light curves can be very, very different. The common property is that their luminosity goes up a lot, so 5 magnitude brightening, but also the overall luminosity goes up to hundreds of solar luminosities. And then accretion rate goes up by orders of magnitude. And then they're long. For example, the prototype F-Ori has been in outbursts for more than 90 years. So if you consider how much material is accreted, that's like 1 Jupiter mass, huge amount of material. And then they also show smaller fluctuations. One important distinction between FUORs and other types of classical T Tauris or other types of eruptive objects is that FUORs are hot in the discrete plane, while other types of stars are hot at the surface. So that causes very pronounced differences in their spectra that we can use to identify and characterize them. As I mentioned, there are long-term variability in fjords, and they're slowly fading. That you can trace at different wavelengths. They also have short-time variability that you can trace with light bursts, and like these may be interpreted as like a signs of binarity or some inhomogeneities in the disks that are orbiting. They also show some spectral variability because these objects may have a variably strong winds, disk winds. They may also vary in their millimeter lines, because when such a big outburst happens, then you heat up the whole disk. And for example, the snow line, which separates the icy grains from the bare grains, moves, and then you may expect a lot of changes in the lines. We have some numerical simulations for this. We didn't manage to get observing time to check this yet, but there are some measurements, at least for the closer objects, that they are really, really rich in different kinds of molecules, which are released from the ice phase because of these outbursts. And then I'm studying the properties of these disks here. I'm showing just how massive they are and how large they are, because I wanted to see whether they are different from normal T Tauri stars, and they seem to be more massive and smaller than normal stars. And that's interesting because then you can check whether they are gravitationally stable or unstable. And this graph shows that everything in this blue region may be gravitationally unstable. So what happens with those disks? They fragment. And then we indeed managed to see this kind of spiral structure, and then these fragments at millimeter wavelengths and scatter light, as well in case of the 960 on one of the objects that is supposed to be unstable. So that's neat. So yeah, I just have two more slides because I haven't talked about intermediate mass stars yet, but they are also variable. And then in this specific case, what we saw with, again, interferometric monitoring is that a new ring appeared in the system, which is interesting because we think that this is due to a giant collision that produced fresh dust. And this is a young star, but apparently the inner disk behaves like a debris disk. And you can see this kind of variability also in debris disks, which are called extreme debris disks, which change significantly their infrared brightness, again, because we think that we have planetesimals that collide, and they produce lots of fragments, and actually also like vaporize part of these planetesimals that condense, and then you get rid of that material, and then it fades back. So you can actually see individual collisions in this system. And then these are my takeaway messages, because I ran out of time. Variability, I hope I could convince you that it's a powerful tool, like a fourth dimension to study these strong young stars, which reveals otherwise unattainable information about the circumstellar matter. If you ignore it, you're probably making a mistake. Thank you very much.
For this talk. Questions from the audience or remotely? Please, go ahead.
From a theoretical hydrodynamical point of view, the accretion charges from the disk to the star, how are they formed? What is the trigger of them? And how do they stop? When do they stop?
Basically, so the main idea of accretion is that you have some kind of way to get rid of angular momentum, and then you have a slow spiral within the disk, which eventually stops because at some point the pressure from the incoming material becomes equal to the magnetic pressure. And then from that point on, the magnetic field will dominate, will determine how the material moves. So that's why it follows the magnetic field lines, and then you have this channel. And then at that point on, mostly it's just gas partly ionized.
Okay, so it's mainly magnetic.
Yes, yes. Yes, at least for normally accreting young stars, For the largest outbursts, the Fe Orionis type stars, we think that the accretion rate is so high that the material completely crushes the magnetic field of the star, and then the material is incoming from the disk onto the star all the way in the mid-plane. So it's a very different process.
Is there another question?
Yeah, actually, I have a question.
Yeah.
This one is about the effect of, I imagine that these objects produce a lot of self-induced local radiation because of the production of crystals, molecules, and so on. So I was wondering what is the effect on the interpretation of your observation in this local radiation and how you can cope with it. The second one is about the impact of luminescence in this kind of science, because as far as I can understand, you need a quite continuous observation of the objects, while the luminosity will have some cadence in the observation. So I was wondering if luminosity in your opinion is still used.
Yes, for the first question, how we deal with the local reddening is difficult, especially, I mean, Ellen knows it very well because we are doing this follow-up of these Gaia errors, where basically we have an object, we have a light curve, we have a few spectra, and then sometimes we have from Gaia a certain distance, which is sometimes well measured, sometimes very, very uncertain, like it can be anywhere between 1 kiloparsec and 3 kiloparsec. Who knows where it is exactly? But in these cases, I mean, what we try to use the spectra to determine the circumstellar reddening by measuring line fluxes, and then basically we try to minimize, and you can use these lines to convert the line luminosity to accretion luminosity. There are like empirical relations between the two, and then if you do this for several lines spanning a certain wavelength range, then you may get different results from the different lines. And if there's a trend in that may be because lines at shorter wavelengths are more extincted, lines at longer wavelengths are less extincted because that's the reddening low. So you can correct for a certain reddening, and then you can minimize determine the reddening, which minimizes the difference of the accretion rates you get from different lines. So that's one way to determine this. If you don't have these kind of lines, or you don't have spectra, then you can try to do this by just projecting back your object to the T Tauri locus. If it's a T Tauri, if it's not very reddened, and then or very embedded, then you can do this in near infrared color diagram. So that's the way. And yeah, in case of the most embedded objects, it's really difficult. So we basically don't see directly the central object, and then yeah, we just assume that okay, most of why we observe as a luminosity comes from reprocessed accretion luminosity. And the second, yes. So for the cadence, I mean, we try to use everything. So even if it's 1 minute cadence, perfect. Even if it's like few years cadence, we try to use it because it traces different kinds of time scales. So, and then basically, if you have lots of observations, which we had, for example, for DR tau, that we are working on now, and then in one of the other papers, CRK, I think we have this graph where you plot like the amplitude of the accretion rate changes as a function of time scale, and then you have the smallest ones at short time scales, which are probably just rotational modulated, and then it increases, and then it flattens out typically, because like these stars can vary as much as, let's say, half magnitude in a few hours or in a few days, but then it's the same phenomena if you look at them like 10 years difference. You just catch them at different states, but they're always doing that. Mm-hmm.
Is there another question?
Following up on that inside of things, I was curious, it sounds from what you're saying that you can use the different wavelengths. You don't need it to always be the same wavelength when you're kind of just compressing.
But it's useful if, I mean, it's super useful if you have some consistent data set that where you can match the different filters, because if you change telescopes, if you have different like spatial resolutions, then that can be difficult, especially. Yeah.
Two observations in 13
Yes, yes, yes. So, I mean, once you have information on the colors of the different processes, like for example, the flares are very, very blue, so their amplitude is very high at UV, in the UV, and then it drops quickly. But like accretion rate variations are more gray. They're a bit blue because it's hot material that you had, but it's, if you go to red optical or near infrared, then it's mostly gray. So if you see less wavelength dependence, then you can assign that to accretion rate variation. So once you have the idea about how to translate one light curve to another, then you can try to do this. It's, in my opinion, it's very dangerous because there can be like delays. And then there's one of these figures that where I cited Anne-Marie Cody's paper. They had a study where they had this huge survey for different star forming regions, Chameleon, Lupus, Taurus, where they compared optical and infrared light curves. And you could classify the objects. These are the objects where the two light curves correlate, and these are the objects have nothing to do with each other. It does something completely different in the optical and in the infrared. In that case, I mean, if you have very different wavelength measurements, then you can't combine them. So yeah, that's why it's important to use the same telescope over and over again. It's difficult to get time.
Other questions? I didn't see any question remotely. So if we don't have more questions for Agnes, I think that we can thank her again. And she will be around today and maybe also tomorrow. We are staying in the first floor office if you want to pass by, and also around Juan and Vera